we are very pleased to have Sara van de Geer here. Sara is a Dutch statistician working in Switzerland for a number of years in ETH Zurich, and she did lots of interesting work and well known in several areas of statistics, you know, and in the last years she has been working a lot on high-dimensional statistics, and she also, you know, well known for many contributions to statistics. She has been for a while the president of Bernoulli Society, now luckily probably former president, right, so you are free now. And we are very glad to have Sara here. So this will be the first lecture here in ASYE, and two others will be on Tuesday and on Thursday next week in the School of Math, so in Skiles. Okay, so you can find everything on the web. Sara, please.
Thank you very much, Vladimir, for inviting me here. It's really nice, and thanks so much for this nice introduction. Okay, let me first say that this is going to be a talk on joint work with Andreas Elsner and Jana Jankova, two of my collaborators. And it will be on sharp Oracle inequalities for non-convex loss. So I thought I'll talk for a while about a case where you do empirical risk minimization. So you minimize some function which is not convex. And I want to show that the behavior of stationary points, but all of this also works. You can forget about the non-convexity and you just look at global minimizers and so on. So, but the stress is a little bit about non-convex loss, and then they'll talk about Oracle inequalities, and I'll have to explain what I mean by that. And sharp Oracle inequalities, I'll explain what I mean by that, and it will be in the high-dimensional situation. Okay, so that's the aim. Some properties, theoretical properties for global minimizers of loss functions which are not very smooth, or smooth loss functions but possibly not convex, and then looking at stationary points. And the idea of the lecture is that it's just trying to develop some unifying theory so that you can handle all kinds of cases in one shot. And so it's theoretical results, it's not developing new methodology, but combining some convex and non-convex optimization with statistical and probabilistic theory. So I'll try to sketch the setup. First of all, there are data, we're statisticians, so there are data around. Observations x1 up to xn. These, well, it's general. They can be in arbitrary spaces, but usually they're just Euclidean spaces. And so there are n observations. And then you want to estimate some parameter, which is some aspect of the distribution of these data. And the parameter space is p-dimensional, and I call it B. And it's a convex subset of some high-dimensional space, so P is very large. And what is the target? So the parameter of interest is somehow defined as the minimizer of some function, which is here, the theoretical risk function. So we have here this red function, and important is that it's not known, because if it would be known, it would be just an optimization problem, but it's an unknown function and you want to find its minimum. And I call that the target beta 0. The 0 is sort of because it's kind of a special point. It's missing here. So I want to find this minimum here, but I don't observe the theoretical risk, that's R. The red function I don't observe. Instead I have my data and I have some estimate of that red function. That's that black function. And because you can observe it, it's called empirical risk. So instead of doing the minimization here, I do it here in the domain where I can observe something. And then hopefully these two functions are close so that the minimizers are close, right? But one of the points in this talk will be that this function here is nice. But your estimator can be non-convex. It can be wiggly. So the picture is not completely correct. But the main idea is that you want to find its minimum, but maybe it's not so easy because it's not convex. So we want to see how close is this to that. And see if it comes back. So now I use my fingerprint, but it doesn't like it. I should maybe turn something off. Well, let's see. I'll go a bit quicker, yeah, quicker than the screensaver. Okay, so far so good. So this is the setup. Now, I didn't really write down how the empirical loss depends on the observations, but anyway, there are n observations, and there are p parameters, and p is much larger than n. That's the high-dimensional case, okay? And then you have to assume something, and typical assumption is sparsity. So you don't really assume it, but it's more like you believe. It's not something you impose, but you hope that the underlying parameter you're trying to estimate is sparse. So there's a lot of noise and nothing going on, but there are only a few non-zero coefficients. So it's saying, well, it's sparse or approximately sparse. So it's approximately some sparse vector, and this vector sparsity means that it has only a few non-zero coefficients. So this is the support set, the active set, and the number, the cardinality of that set is S, and S stands for sparsity, and it's sparse, meaning that S is somehow small. Or it can be that many of the coefficients are almost zero, but let's not worry too much about that. You can have some kind of weak sparsity. Okay, then we consider a situation where this theoretical loss function is convex. That's that red function. The unknown function is convex, but we don't know it. And the empirical loss function, that's the one with the hat, is observed, but it's possibly not differentiable or possibly not convex. It may have multiple local minima. Okay, now the aim. I'll give you a couple of examples to see what I'm thinking about. So again, high dimensions. So we have here a regression model with a response variable y and a covariance matrix, a matrix of covariables, so a design matrix X. And you can do a linear regression of y on x, so saying y is a linear combination of x, of the columns of x plus error. And so if p is larger than n, so the number of parameters is the coefficients in the linear combination, it's large. So we do a linear combination, take the approximation, and now we measure it in terms of the absolute values, so not least squares, but absolute values. And then you end up with an empirical risk function. And it's, well, you can say it's differentiable because it's only not differentiable in a couple of points. Well, the absolute value function is not differentiable, but anyway, it's not a very smooth function. If you would say, okay, if I look at the derivative, it's more or less the sine function, which is jumping, so that's definitely not smooth. So this is not a very smooth function. That's an example of a convex, but not very smooth function. Here's an example, very simple, of a smooth function, which is not convex. That's the errors in variables model. And suppose you again want to do a linear regression. Y is a linear function of x plus error. Error is say, just standard Gaussian or whatever, not very difficult. But you observe y, but you don't observe x. You observe it with error. And the error is independent of x, and let's say with a known covariance matrix. Okay, so now if you do least squares, if you would know x, you could do least squares, right? And then you would do something like this. Let me just write it up, just to be sure that we get something simple. So you do just least squares. So you minimize this over b, you get the least squares estimator. let's see, plus, minus 2. And I call that sigma hat. Well, I normalize with n. So this would be the minimum. If you do least squares, you would minimize this, right? And what occurs is the ground matrix of the x's and a linear term. And this term you don't care about, but doesn't depend on the parameter over which you're minimizing. So I'm doing exactly that, but now with the errors in variables model. So I replaced the x by what I observe, which is z. And then this quadratic term, there I replace this gram matrix, which I don't observe, by an unbiased estimator. So I just take the gram matrix of z, what I do observe, I subtract the unknown the covariance matrix of the errors, and then I get an unbiased estimator of this one here. Yeah, so that's very standard procedure. A little bit naive maybe, but this is what you do. But anyway, if you know that this matrix is going to be positive semi-definite, but if you subtract a positive semi-definite matrix, you possibly get something which is no longer positive semi-definite. Yeah? No guarantee whatsoever. So this is a non-convex loss function. So if you minimize this one, you get, well, you don't know how to minimize it in fact, in practice. Another example is principal components. Then you observe a data matrix with n rows, p columns, and you're trying to estimate, well, this is the ground matrix. You're trying to estimate the first principal component of the covariance matrix, say. So say, think this is a matrix with IID rows, and each row has a certain covariance matrix, and you want to estimate the first principal component. Then you could do it like this, just do the best rank 1 approximation. And that's again a non-convex problem here. Okay, and we'll study it in high dimensions where p is larger than n, so we also need to add a regularization there. Yeah, so these are some examples of non-convex problems. Another example is, suppose you want to do one-step Newton-Raphson, then you need the matrix of second derivatives of the function you're looking at, and you need to invert it. And in high dimensions, you can be, you have to be very lucky. In general, you can't do that because the matrix will be singular and it will not even be positive semi-definite. So inverting that matrix can be, well, you just can't invert it, but you can try to do some kind of surrogate inverse by doing some kind of regularized projection. So inverting a matrix is just like projecting each variable on all the others. But now you can't do it, but you can do this sort of kind of regularized projection. But anyway, this will be a non-convex problem as well. Okay. So this is our aim. Maybe I should have a clock. So we want to extend theory to sharp Oracle inequalities. So then I have to explain what I mean by sharp. When the risk is not so smooth or not convex. And there is some work, especially for these non-convex problems. So the new element in this work is the sharpness of the result, which sort of helps you when you have model misspecification or when you have a learning point of view. And the theoretical elements of it all are just based on work by Vladimir and Karim Lunici, who was also here. So they're very important also for this work, and the colleague Sasha Chibakov. Okay. So first let me explain what is a sharp Oracle. Okay. First I explain what is sharp in a sharp Oracle inequality, and then explain what is Oracle. Okay? Now, a sharp oracle inequality is of the following form. So you have this red function, this unknown function. You want to minimize it. Or maybe you're minimizing it over a subset of the Euclidean space, and maybe the true minimum is not in that set. So you want to get the best possible approximation. So you want to minimize, this function over the parameter space, the best possible, and then a remainder term. And so you don't really have a model. You just want to have the best possible approximation of the minimal risk. So that's not really taking a model into account. You're not thinking of a true parameter and so on and so on. You just want to minimize a function. And that's sharp. So to see what it means, if you look at this, you can, the true target, so the real minimizer could be beta 0. You can, of course, subtract on both sides here any constant. And then it doesn't, the result is just the same. It cancels again, and so it's the same. So I subtract this constant here. What you get here is then called the excess risk. And here another excess risk. So then nothing changes. But here, you can now think of having results where there's a constant in front of the excess risk, which is larger than 1. And that's not such a problem if you think asymptotically and so on. But if you have a misspecified model, it can be that the best approximation in your class is still far away from the true minimizer, so that this, in asymptotic setups, will not be small. We will not go to 0. And if this doesn't go to 0, and a constant bigger than 1 in front, then it's just a useless result. Right? So sharpness means that you can have this not going to 0 and still have a nice result. Just forget about getting close to this one, just getting close to the best minimizer. Okay? That means sharps. So that's a type of learning point of view. You don't really have to start with a statistical model and then hope the model is true, but you just define your parameter in your goal like this. The goal is defined like this. Then the oracle part is about the remainder. The remainder should be, of course, nice. Okay? So let me see. What's an oracle inequality? That says the remainder should be more or less the number of active parameters divided by the number of observations. And so the number of observations is n in my notation, and the number of active parameters is the sparsity. Okay? So why is that a good idea? Well, you can think of regression or something. Typically, depending on all kinds of situations, we'll see that. But typically, you need per parameter 1 observation. So this would be the good behavior. And in this case, you don't know how many really parameters there are. Well, active parameters. You start with p parameters, but only s of them are active. And you don't know that a priori. So if you can achieve this goal, it's really like an oracle. An oracle is somebody or an algorithm that behaves as if you know what are the active parameters, but we don't know it. We just have no idea. But still you get this kind of good behavior in the remainder. That's as if you are the oracle, as if you have heard an oracle tell you what to do. So S is the number of active parameters. Well, maybe, again, this is a learning point of view, so maybe you're outside the parameter space, so you have misspecification, and then you just take the best approximation and the sparsity of that. And so that's the kind of benchmark we want to achieve. But then there's an approximate sign here. And this approximate sign, what does it mean? It means, first of all, that, well, we don't know. Reaching the oracle is, of course, a bit too much to ask for. So the penalty or the price to pay is that we don't know the active set is logarithmic in terms of the original number of parameters. There will be an additional log p term here occurring. And the second thing is the sparsity S. We have to replace it by effective sparsity, which I denote by gamma squared. I have to explain what that is. But you can imagine that somehow you need some kind of identifiability of these parameters. So depending on how well identified you are, you will get close to this benchmark. So you somehow have to take into account some identifiability, which will typically make the effective sparsity a little bit larger than this naive idea of sparsity, just the number of non-zero parameters. It's a little bit more complicated, the concept. Okay, is that so you know where we're heading at now? Okay, now what do we do? Yeah, there's a question.
Did you say what gamma was?
No, I will not probably say much. I'll say a little bit about it, but it's a separate lecture more or less. I'll give an idea. Yeah. So this is like a preview of what will come. Yeah. Okay. And then the estimator will be the following. So we take the empirical risk. Think of the one I just wrote for the errors in variables model or the sparse principal components or least absolute deviations. That's the empirical risk. And because of the high dimensional problem, we take a penalty, which will be a norm. In most of my talk, it will be just the L1 norm to fix ideas, but it can be general norm. And lambda is a tuning parameter. If you take it large, you will have more regularization. And if you take it 0, if you don't penalize, and you minimize this function, or you take stationary points, then you're in trouble because you have so many parameters, and then you will overfit. Okay, so to have a regularization here is really important in high dimensions. Good. Okay, so now in principle, what we want to do as an estimator is to minimize this function. And then we get a random quantity, an estimator of the target. Now minimizing this function you can do as follows. You just take the derivative and put it to 0. So we're in Euclidean space, nothing special, we can just take derivatives. So I'm going to define what a derivative is. And because putting it to 0, if you solve that, you get stationary points or the true minimizer. You have to define what is the derivative. Well, here usually there's less problems, especially if this function is differentiable. But the derivative of a norm, I have to define that. So that's one of the tasks, define stationary points. That's to come, and then we have to define curvature. Maybe just go back quickly to the picture. Here we go. So we have this function that we are going to minimize. Well, we're trying to minimize. We are minimizing the black one, but the red one is the theoretical risk. And we're thinking about finding this minimum. And you can imagine if there's more curvature, the problem gets easier. And if the function is very flat, the problem is more difficult. So you have to somehow quantify that in terms of the curvature. And that's here. So we quantify that curvature, and then we measure the distance between 2 points in the parameter space. Well, you can take a Euclidean distance, but in many cases you have to take some other distance because it's more natural. So we measure distances in terms of some norm, tau. So now we have two norms. One for defining curvature, and one here as a penalty. So now our third task, so this first gives some identifiability in terms of a norm tau, and then we have to relate this norm with the norm occurring in the penalty, and that's where effective sparsity comes in. This is a type of norm comparison going on. So let me do that. Let me first define stationary points. Well, if you just do global minimization, if you could do that, you just do what you do. You just minimize it. So I call that the arc min solution, beta hat. But for stationary points, I have to find the derivatives. So you need the derivative of a norm. And here it is. You need, it's not the derivative, it's the subdifferential. So if you're not familiar with it, it's no problem at all. But just that you know that you can sort of take the derivative of the norm. And it involves the dual norm. And if you're a little bit more familiar, or if you're curious, here's an example. If you take the L1 norm, that's the sum of the absolute value of the coefficients. Then it's like taking the derivative of the absolute value function. It's here. And then the derivative is here is -1, and here it's +1. And in this point, it's not differentiable. And then the subdifferentiable is just any value between -1 and +1. It's this whole interval. And that's written here. So this is the subdifferential of the L1 norm. Just what I said. And you can do that for other norms as well. This kind of, what occurs here is the dual norm. I'm not here the L1 norm, and the dual norm is the L infinity norm. Okay. Anyway, so you can define that. And then you have the subdifferential, and you just take your, assuming that your risk function, empirical risk function is differentiable, you take the derivative, and you take the derivative of the norm, and you put it to 0, and you solve, and then you get a stationary point. That's how a stationary point is defined. Okay? And because of the parameter space can be just some bounded subset of the Euclidean space, you can be at the boundary. So let me make it a little bit more general to take that into account, but don't worry about that. So more or less, this is a little bit more general than this. If you have this inequality where we say we have a stationary point. Okay. And here this beta is arbitrary in fact, but we just write here for some beta, which will be the best sparse approximation later on. So the oracle, so to speak. So if you have a global minimizer, you have a stationary point, but not the other way around. Clear? That's true. Okay, so that's the stationary point. Now this curvature and effective sparsity. Well, let's first look at this curvature. We're going to assume, so that's conditions on the theoretical risk, the underlying unknown risk function. We assume it to be convex, but having a certain amount of convexity. Okay. Now let's see. So like I said, I take some norm on the parameter space. Well, it's the subset of the Euclidean space. I take a strictly convex function. And then I'm saying the function, the risk function is strictly convex. Well, here is if convexity. Convexity is if you take a convex combination, 1 minus t times b plus t times beta. The risk is then smaller than the convex combinations of the risks. That's convexity. And to quantify how convex, you have here minus what? Minus something. And there comes something which describes the amount of convexity, so to speak. So there's some function here, which will be large if you're further away from B. So if this is large, this will be large. Okay. And you see the norm, you measure the distance between the points in this norm tau. Okay, so don't worry too much about all the details, but just the idea, this is the description of amount of convexity. And we call that strict convexity. This I will need for, so here there are no derivatives involved, and I'll use strict convexity if you cannot differentiate. If you can differentiate, I'm going to look at the linear approximation, the difference between the original function and its linear approximation, and that has to be lower bounded by some convex function. I call that Bragman condition. It probably has some name. So if you have this difference approximation by a linear function with the derivative, so you have to assume it exists. And the difference between this and this is called the Bregman divergence. And I assume this Bregman divergence is lower bounded by some convex function. Okay, yeah. So just a description of curvature. Yeah.
Can you include? Oh, sorry. So that was the description.
This is the description. This is my description of curvature. Yeah, and typically, in my example, this function will be quadratic, like a first order two-term Taylor expansion. But it can be something else. You have lots of examples where it's different. So if it's something like x to the power 1 plus delta, then you have less curvature than when it's x to the power 2. Quadratic is like the standard case. And this the Bregman divergence is here. You have a function. You take a point. I call it beta hat here. You take the linear approximation, and then there's a difference here, and it's called the Bregman divergence. Now this is in one dimension. In higher dimensions, it's a little bit more complicated to draw. Yeah, so let's see. Now I'm going to restrict myself to just this particular norm, the L1 norm, and later on I'll just tell you that you can extend it to general norms, but just not because we already have enough technical details. Let me just restrict myself first. So the norm in the penalty is now the L1 norm, and I need some notation. Why do I need this notation? Well, to define this effective sparsity. Yeah. Okay, so take an arbitrary subset of the variables. And then I'm going to denote by Bs and B minus as the following. So here's an example. I have an arbitrary vector. And I take some subset, 2, 3, 7, 2, 3, 7. I don't touch them. And all the others I put to 0. So just restricting myself to this subset of the variables. And I denote that with Bs. And B minus S is the same, but now on the complements. So you put this, you leave this one untouched. And these three are now untouched, and the other ones are put to 0. Okay, so that's just a convenient notation. Hope that's okay. And then the effective sparsity, so here comes the whole story. People have been working on this quite a while. But the effective sparsity, which I define now, is just comparing the L1 norm in the penalty with the norm appearing in the curvature. A few words, just a few words. If you look at the literature, it's often a little bit differently described with terms like restricted eigenvalues or RIP, restricted isometry property. I call it compatibility constant, and on Tuesday next week I'll talk about it, and actually you can even refine the things and so on so that you get really good results. But in this setup, geometrically it would be something like an L1 version of canonical correlation. It has to be something with correlations or eigenvalues. So the effective sparsity is just a number of non-zero coefficients divided by some number which can be very small, which can blow up the whole thing, the gamma. And here's a geometric picture of effective sparsity. So here the active set, so the set S is just the first variable, and these are all the other variables. You take the signed convex hull, and then the distance to this signed convex hull. That's this number here. So if that distance is very small, the effective sparsity will be very large. Okay. So that's, yeah, sorry?
I missed the tau 2, that's the curvature? No, what is tau 2?
Yeah, tau 2 is that's a good question, that's this one. So I measure the curvature in terms of that one. Yeah. Yes, exactly. So typically tau will be just a Euclidean norm, but often it's just there's some weighted Euclidean norm. So yeah. Okay. Now this is the main result for the non-differentiable but convex case. So take the global minimum. Let's for simplicity say that the curvature is quadratic. And then comes a condition which has nothing to do with that, but this is the noise level. So every probabilistic argument is hiding here, so we're zooming out. It just says, I have this empirical risk and I have the theoretical risk. How far are they from each other? In some sense, don't worry, but in some sense, and that's called the noise level. Okay, so to deal with this, you need lots of probabilistic arguments. But once you have that, once you can say, okay, this is something random, if it's less than that with large probability, okay, I call that the noise level, and I take my tuning parameter larger than the noise level, and then I have this sharp oracle result. So there's a constant 1 here. The risk at the estimator is the global minimizer. It's bound by the risk at beta, so you can do it for any beta and then minimize over beta plus effective sparsity times tuning parameter, more or less, squared. The squares are because of the quadratic margin, so the quadratic curvature. Okay. Now just the flavor of the result. So the hard thing is, of course, hiding here. Otherwise, it's quite clear what's said. But typically, the noise level is of order square root log p over n. And then if the effective sparsity is also more or less the true sparsity, then you get the result is, well, here, the difference is of order, well, log p over n, that's this. You get the log p over n times the active number of active parameters. So you see that you achieve this benchmark, and that you have this sharp oracle result. Yeah? I don't know why I should. If this is true with high probability, then this is true with the same high probability. Okay, so this is like a deterministic statement. This will be true with some probability, and then this will be true on that set as well. Okay. Okay. So that didn't assume any differentiability, but it did assume that you have the global minimum. If you don't have the global minimum, then we assume this stronger. What do we do? No, a less. So if we assume differentiability, we typically have a less strong condition for the curvature, and you only need stationary points. So you have just any solution of putting the whole thing to 0. And for any of those solutions, you have a sharp oracle result. Just exactly the same as in the previous slide. And the noise level is again comparing the empirical risk with the theoretical risk, but now not so much the originals, but their derivatives, comparing their derivatives. Yeah. If we look a little bit back here, maybe here. This was if they're not differentiable. And what I then do for the differentiable case, I just let t go to 1 or 0. I'm not sure. I think to 0. And then you get the derivative. But if it's not differentiable, I just don't go all the way down to 0. Okay.
Excuse me?
Yeah.
So in the last line, like why are you putting active parameters by number of observations? Because you have already computed the effective sparsity, which has taken like the differentiable of like penalty versus the differentiable. So
Yeah. So this remainder. The remainder. Let me see. Good question. Is something like lambda squared times gamma squared, and then lambda squared is of order log p over n, typical cases, and gamma squared, did not write it, but it's the flavor. The flavor of the result is that you should think of this as S. Okay, that's the idea. Is that okay? So actually what is there is the effective sparsity. It can be much larger. But in most examples, people always try to prove things like this, trying to prove that this is of this order. Yeah. But if it's not, then, well, then it's just, you don't have this nice oracle result. Yeah. Okay.
So which is difficult to compute more, effective sparsity or finding the number of active parameters by number of observations? Or
well, this effective sparsity is difficult to compute. And on Tuesday, I'll give an example where I can compute it explicitly. That's for total variation penalty. And in other cases, people just do some design which is random or so, and then say with high probability they are of a certain order. So it really actually computing effective sparsity is very hard, I think, is in my experience. You just have bounds and arguments coming from randomization and things like that. Yeah. Okay, so you have both these theorems, one for the non-differentiable case and one for the non-convex case. They're the same flavor. And in general, if you have a curvature with some general curvature function, what instead of quadratic, something more general, what appears in the bounds is just, if you want to know the convex conjugate instead of the square. So the square is the most standard case, like a two-term Taylor expansion. Then the convex conjugate is also the square. Okay, now let's see. How much time do I have? Something like 15 minutes? Hmm? Okay, so I'll just go quickly through this. So there is this random part of the problem. And I call that the empirical process condition. Just an idea. So if you do, for instance, generalized linear models, then you have some observations x and y, and you want to approximate y by a linear combination of the x's, maybe with some link function and whatever. Anyway, then you have a loss function rho. If this loss function is Lipschitz, we call it assumption Lipschitz. And if its derivative is Lipschitz, we call it the assumption derivative Lipschitz. And in both cases, if you do the global minimizer and you have just Lipschitz loss function, you get the noise level square root log p over n. If you have a stationary point and a derivative Lipschitz function, then you get a noise level again square root log p over n. This is just standard empirical process theory. If you know it, it's just applying those tools. And so you get indeed this order for the random part. Okay, so just a conclusion, if you have these generalized linear models, if the loss function is Lipschitz, you get sharp oracle inequalities for the global minimizer. And that's for the convex case useful because you can only find it then. And if the loss function, its derivative is also Lipschitz, then you have sharp oracle inequalities for stationary points. And that's useful for the non-convex case.
Can I ask a very basic question?
Yes, of course.
So there, the number of active parameters is important here.
Yeah.
And that's just the number of non-zero parameters?
Oh yes, that's a good question. So what I'm saying is S is the number of non-zero parameters, but you can also have weak sparsity assumptions. But just not to go to too many special cases, but you can also have something like that you look at this, let me call it R or something. Even with R equal 1, you can prove things. But anyway, something R between 0 and 1, and assuming that this number is of order, I don't remember, something like this, where S is small order n over log p. These kind of assumptions, then the theory goes through. And R equals 0, that's a special case, then you have the number of non-zero parameters. And so, This is sort of a strong sparsity and this is a weaker form. But the theory goes through. You just have to do some kind of trade-off in approximating a vector like this by a vector like this, and then the approximation error is being of the right order, and then the whole theory goes through. Yeah, that's a good question, especially if you do function theory or something. Then you typically have this kind of weak sparsity. Yeah? If you have functions in some Basel space, you do these kinds of sparsities and not a strong one. Yeah.
Okay, and scaling doesn't matter, so somehow...
The scaling, it depends on the model, but typically you assume that the L2 norm of the vector is bounded. So that you scale it like that, something like that. But it depends a little bit. Yeah. Yeah, that's a good question. Of course, you need some scaling. Yeah, that's true. It's hiding. So least absolute deviations in high dimensions. If you do least absolute deviations, the loss function is like this. And the derivative is like the sine function, but it's definitely not Lipschitz. So you're not in the derivative Lipschitz case, you're in this not so smooth case. But okay, so then you need global minimizers and stationary points. I don't know how to prove something for that, but it's convex, so exactly. So it's convex, so it's no problem. So let me just go. Okay, here's the result. So you have, for least absolute deviation, you have a sharp oracle inequality, where the effective sparsity is more in standard literature. It's more or less expressed in this form, but it's the same thing. So the norm used in the curvature condition is just some kind of weighted L2 norm. All right. You can apply this to sparse principal components. Just in view of time, what you have to do is first get in a local neighborhood, so that in that local neighborhood the theoretical loss is convex, but the empirical loss is still not convex. But let's see. So we take this loss function, the Gram matrix, and so the empirical covariance matrix, and do the best sparse approximation, and then with the L1 penalty. Okay, then you have to check the conditions. It involves some random quadratic form, so a little bit random matrix theory to get the random part right. But in the end, applying the theory, effective sparsity of the same order as the true sparsity, and you get this kind of result for sparse principal components. Also, this is just a lot of blah blah, that you can do these kind of arguments to go further, and even for sparse principal components, if you do a one-step Newton-Raphson estimator, you can prove asymptotic normality. It involves again these same arguments for the non-convex loss, because the Hessian is not going to be positive definite. Okay, this is just to convince you that everything goes through for general norms. So let omega be some norm. Let's look at some empirical risk and then penalize by this norm. And then minimize that. It's the arc-min estimator. Or you can look at stationary points. We know how they are defined. So if you do the global minimizer, we assume strict convexity. Otherwise, this Bregman condition. So everything goes through, except that it's now a general norm. So the norm we want to be inducing sparsity, because we are thinking about sparsity. And inducing sparsity, you can check that in a way, is the same as assuming some kind of decomposability or some kind of reverse triangle property. So I can't really say any details here, but just convince you that the whole theory goes through if you have the proper structure in your norm, which induces sparsity. That's written here. And then you see here the effective sparsity, which is again this norm comparison. So everything is the same, and the theory is also the same. So this is completely the same, but now for general norms. Good. So you have these sharp oracle inequalities. Here are some examples of norms. The L1 norm, this is like an earlier version of the slope. The sorted L1 norm, or the slope, maybe you know these things. You have norms generated from cones. I won't give the details, but this is like a structured sparsity. And nuclear norms, and the generalization to tensors. So these are the norms I know. Maybe you know other norms. And they also have this right sparsity-inducing property. So let's see. For instance, if you do matrix completion, you can do it with robust loss. And then for matrix completion, you use the nuclear norm or the trace norm. Yeah, so you have some matrix, and you observe only certain entries. You assume the matrix has low rank. That's the sparsity in the principal components. And you observe x times b, so you observe certain entries. I'm just going quickly at this. And then you, instead of least squares, you now do robust versions. For instance, you take as loss function least absolute deviations or Huber loss. And then, well, apply the theory and you get, yeah, you have to do the random part. The random part is a bit difficult, but it's doable. You have to look at, actually it's quite standard, but you end up with, yeah. The dual norm of the nuclear norm is the maximal eigenvalue of a matrix, and so you end up with maximal eigenvalues of random matrices, but they are well studied. Good. So you just go through all these conditions, and you end up with the following result. So for a robust matrix completion, an oracle inequality, and the remainder is the number of non-zero parameters divided by sample size and a logarithmic price. And what's this number of parameters? Well, if you have a matrix of rank S, and it's a P1 times P2 matrix, say P1 is the largest of the two, the number of rows, then the number of parameters is more or less P1 times the rank of the matrix. And so this is just, again, number of parameters divided by number of observations in the remainder. And so it's the usual structure.
So this looks like a kind of entropy measure?
Oh, sure. Yes. Yes. Yeah, no, the dimension is an entropy measure, sure. Yeah. Very good, yeah. So let me conclude. Last part was a bit quick, but the conclusion is, so the idea is just that you can do this in a very general framework. Oracle inequalities which are sharp, allowing you so for model misspecification, allowing for non-convexity, although you do assume that the underlying function is convex. It's an unknown theoretical risk. You get them in high dimensions as long as these norms are sparsity inducing. So people call it decomposability or Tarangle property. So as long as you have enough curvature of the risk. And this effective sparsity, I didn't really explain what it is. I give some hint. A measure of effective sparsity. These are the ingredients. And then you have these oracle inequalities, and then it applies to several models. Least absolute deviations, errors in variables, principal component analysis. So Tukey loss is a very nice example of non-convex loss. Robust matrix completion, matrix slope, and that's an example. I didn't show it. And this is important for estimating for one-step Newton-Raphson type procedure. And I'll talk about that part, estimating the inverse of a matrix, on Thursday next week. I'll just not in this very general context, but this is useful for getting, well, for constructing new estimators from destructured estimators, which are asymptotically normal, so that you can build confidence intervals. Okay, I want to thank you very much for your patience and hope that there will be questions.
Any questions?
Yes.
So, I think you know this very well. Jianqing fan has this scat penalty,
Yeah.
which is actually non-convex. So it's curious. It doesn't seem to fit into the framework. That
No, it doesn't fit. No, there's you can prove Oracle inequalities, but not sharp. Let me give you the reference. This, by Po Ling and so on here. They do these kind of scat penalties, but you will not end up with sharp Oracle inequalities. So, and I'm pretty much convinced that it's impossible to do anything like that in that with scat or something. No.
More questions? I maybe have a very quick question, with this type of parameters as gamma 2, say, right? I think if you are in more restricted framework where you have, for instance, something like, I don't know, restricted isometry condition or something like this, you probably can show with some minimax lower bounds that you're getting correct rate right here. Are there any minimax results that would show you that such that gamma 2 will appear in the lower bound, say, or something like gamma?
Okay, so there are two ways you can think of this. So for minimax, well, there are results which say that, well, not minimax, but by Martin Wainwright and co-authors, that if you do the Lasso, then for a polynomial time algorithm, it has to appear also in the lower bound, the gamma 2.
Polynomial time, so it's related to computational complexity.
Exactly. So it's like a computational lower bound, computational minimax lower, whatever. You can also just, and I'll talk about that on Tuesday, just look at the algorithm itself, the Lasso, I'll look at it. And then you can show that it depends a little bit on the underlying parameter, but then that it's also in the lower bound, just for this particular estimator, that you can't improve. Yeah.
Tuesday, by the way, the next 2 lectures are back in Sara.
Oh yeah, so, okay, so any more questions? If not, then we are done for today, and the next 2 lectures will be in the School of Mathematics and Scale, so that you can find on the web, precisely the room. I don't. It's either 006 or 005. It's all.
It's all 6.
And they are one next to another. So. Okay, thank you again.